All right, we're on problem 15 here. So let's let f of x be equal to 2x minus 1 divided by x minus 4. In part A, we want to find f of 2. So when x is 2, what is f of 2? Okay, well, if I replace x with 2, we had 2 times 2 minus 1 divided by 2 minus 4. 2 times 2 is 4, minus 1 is 3, and then 2 minus 4 is negative 2. Okay, so negative 3 halves, or negative 1 and a half, that'd be the answer to part A. In part B, we want to find f of a plus 4. So just like with part A, we need to plug in a plus 4 where we see x. Okay, so let's do that. We got 2 times a plus 4 minus 1 divided by a plus 4 minus 4. A plus 4 minus 4 is a. And then when I distribute up top, I got 2a plus 8 minus 1. 8 minus 1 is 7. So 2a plus 7 divided by a, that would be the answer there. And that'd be as simplified as I can get things. Okay, and you know, something that I've already mentioned, but you know, simplify everything as far as possible here. Okay. Well, if you try part C, if it's possible, find f of 4. Okay. Well, I know in math I can't divide by 0, right? Division by 0 is not allowed. So if x is 4, I get 0 down under. That's bad. Okay, so 4 would not be in the domain of this function. The domain is all the input values, and the range is all the output values. Okay, so f of 4 would be undefined. Okay, you can't plug 4 into the function there. Now in part D, they want us to state the domain of f. Okay, so what are all the numbers that you can plug into this function? Well, I have what's called a rational function. You're going to do some things with rational functions in chapter 4. And the only thing that I'm interested in with this is that I can't divide by 0. Okay, so 4 is going to be the only number that makes 0 happen in the denominator. So using set notation, I would have the set of all numbers x such that x is not equal to 4. Okay, any other number is okay to use as an input value. Okay. In problem 16, we want to state the domain of each function. Right, your answer is using set builder notation or interval notation. Okay. In part A, I have the function f of x equal x cubed plus 4x minus 1. So what are all the numbers that I can plug in for x? Well, this function is saying pick a number. It can be any number. Whatever number that is, you're going to cube that number. You're going to add 4 times that number and then subtract 1. Okay, well, I can do that to any number I want, right? So the domain is going to be all real numbers. Okay, a capital script R represents the set of all real numbers there. Okay. Part B, I got g of x equals 2x plus 6 divided by 3x minus 4. Okay. This is a rational function. Again, you're going to do some things with rational functions in chapter 4. Rational function is just a fancy word for a fraction, right? I know I can't divide by 0. So on the side, you know, if I set this equal to 0 and solve, let's see, I got 3x minus 4 equals 0. When I add 4 and divide by 3, it looks like x is 4/3. Okay, now that's what I don't want. I don't want 4/3. Okay, so x can be any number, just not 4/3. Okay, and using set notation, I would say the set of all x such that x is not equal to 4/3. Part C, I have h of x equals 2x divided by x squared minus 9. Okay, well, I know I can't divide by 0. So let's go ahead and set the denominator equal to 0 and solve for x. Okay, I got x squared minus 9 equals 0. When I solve that for x, I'm going to add 9 to both sides. I got x squared equals 9, and then take the square root of both sides. So whenever I take the square root of both sides in an equation, I always have to tack on a plus and minus on the right side. Don't forget about that necessary step in solving for x, okay? Because I'll have people say that, x is 3, and then they'll just circle 3. No, you only got half the answer, which is a wrong answer, right? So x can't be 3, and x can't be negative 3, okay? So any other number, just not those two numbers, is going to be okay. Part D, k of x equals 2x divided by x squared plus 9. Okay, well, I'm interested in the denominator here. I know that the denominator can't be 0. So will it ever happen if x squared plus 9 is 0? Okay, well, will that ever happen there? Well, if I subtract 9 from both sides, I get x squared equals negative 9. And now, no matter what x is, if I square any number, I'll never have a negative, right? So I got a positive equals negative 9. That's not true, okay? So x can be anything in this function. The domain is all real numbers. Okay, now a little later on in chapter 4, we're going to learn about imaginary numbers, but all we care about are the real numbers. So x can be any real number, and you can plug that in to k. All right. Part E, we have f of x equals 5x minus 1 divided by x squared plus 4x minus 5. Okay, well, the denominator can't be 0. So if I set the denominator equal to 0, this should factor. It's going to be x plus 5 times x minus 1. And I can check that. X times x is x squared. Negative 4x plus 5x, negative x plus 5x is 4x in the middle. And then 5 times negative 1 is negative 5 at the end. Okay, and then when I set each of these equal to 0, x plus 5 equals 0 means that x is negative 5. That's what I don't want. And x minus 1 equals 0 means that x is 1. That's what I don't want. So x can be any number. Just don't take negative 5 and 1. Okay, that'd be the domain. Part F, we got the function g of x equals the square root of 1 minus x. So, well, let's see. I know by my rules of radicals that I don't want a negative overall number underneath the square root sign, because the square root of a negative is not a real number. And we're going to learn more about that in chapter 4. Okay? So, if I just go on the side here and set 1 minus x to be not a negative, or to be greater than or equal to 0, and then I solve that, if I add x to both sides, it looks like x has to be some number that is less than or equal to 1. Okay? So any number that is 1 or less is going to be okay. If x is 2, I don't want that, right? Because 1 minus 2, that's negative 1. The square root of negative 1, that's not a real number. Okay? Use set notation or interval notation is fine also. If I were to write this as an interval, anything that's less than or equal to 1 would be the interval negative infinity to 1 with a bracket by 1, right? Because you're including 1. Part H. So part G, sorry. I got h of x equals the square root of x squared plus 5. So what is the domain of that? Well, again, what I said here is that anything underneath the square root sign can't be a negative. Okay, so just if I go on the side and I set x squared plus 5 to be greater than or equal to 0, and then I solve this, subtract 5 from both sides, x squared is greater than or equal to negative 5. Now, I know that if I square any number, I never have a negative, right? So will it ever happen for x squared plus 5 to be a negative? No, right? Because this statement here is always going to be true no matter what x is. You're always going to have x squared be greater than or equal to negative 5, right? So the domain would be all real numbers. Okay, and remember that for the set of all real numbers, like there's a couple of different ways to write that down. We saw that up here, using set notation or interval notation, that's fine. Or you can use the capital script R, that's fine. Okay, or you can write out in words, as all real numbers, that means the same thing. Okay. And then part H, let's see, I got k of x equals the square root of x plus 3 divided by x plus 1. Okay, what is the domain of k? Well, I know I can't divide by 0. Okay, so x can't be negative 1, because negative 1 plus 1 creates 0 in the denominator. Okay, so throw away negative 1. Also, I see the square root expression up top, and I know I can't have a negative underneath the square root sign. Okay, so the square root of x plus 3, that's what I got there, x plus 3 can't be a negative, so if I set that to be greater than or equal to 0 and then solve for x, subtract 3, so it looks like anything that's negative 3 or more is going to be okay. Just I can use any number that is greater than or equal to negative 3, but not negative 1, I said, because of the denominator. Okay. So that'd be that guy there. All right, why don't we go ahead and stop the video right here, and I'll pick up with problem 17 in the next one.